Okay, so let me begin. I decided to talk about something that is that I've been working on off and on for several years, mainly because there are many aspects of it that are both fascinating and interesting, and also things I don't quite understand. So the topic is exceptional points in time-delayed systems, and I want to acknowledge former PhD students Joe Sulzer, Andrew Wilkie, and Brendan Glover, who at various points contributed to this work, and a former colleague of mine who's no longer at my institution, Professor Yogesh Joglekar. And this work was supported by, and is continuing to be supported by the Air Force, for which we are very grateful. So let me first, what I'm going to do is there are two buzzwords in this title. There's this whole time-delayed system, and then there is this term exceptional points. So let me begin there. So what do I mean by time-delayed systems? So let us start with this familiar differential equation. This is the linear decay equation that we encounter in undergraduate physics very early on. And one of the ways that we are told to solve differential equations is, okay, let me assume a series solution. And if I plug that solution back in here, I get the characteristic equation. And then we know that the solution is given by this eigenvalue is equal to negative gamma. But now if I take that same equation and I say, okay, what if the derivative of x depends not on the instantaneous value of x, but on the value of x at some earlier time tau? And these such systems are also referred to as non-Markovian systems, but this is where the time delay is. And the key is that the instantaneous value of the derivative, it depends upon the previous value. And so the system has a memory of what happened to it sometime prior. Now, if I use the same series solution technique and I plug in an assumed solution, I end up with an eigenvalue equation, which you can see is transcendental. There's a lambda on the left, there's a lambda on the right. And so such transcendental equations can have an infinite number of solutions. And so the moment I go from sort of our standard linear decay equation to something that is time delayed, now one has an infinite dimensional system. And such systems can have a very complex behavior. If you're a student who's hearing this for the first time, you should just put this on a computer and solve this for, you have two variables, a, which is a constant, and you have a tau, which is a time delay. You'll find that if you put this on a computer, and you have to because there are no analytic solutions for such equations, you'll find a wide variety of behaviors as opposed to this system, which of course, as you know, is just an exponential decay. Exceptional points, these are properties of non-Hermitian matrices. Okay, so it has nothing to do with quantum mechanics, or even though it comes up frequently in the context of physics, these are properties of non-Hermitian matrices. So it's purely a mathematical entity. But what it means is that if you have a non-Hermitian matrix, then under some conditions, if the eigenvalues are degenerate, and the corresponding eigenvectors are also degenerate, then we refer to these parameters as exceptional points. So as you know, a Hermitian Hamiltonian or a Hermitian matrix will have eigenvectors which are perpendicular to each other. Now, these two perpendicular eigenvectors, if you have a non-Hermitian Hamiltonian, and these two eigenvectors become parallel to each other, we refer to that. And the eigenvalues are degenerate, we call that an exceptional point. Now, such non-Hermitian Hamiltonians arise frequently in the context of quantum mechanics of open systems. When we teach physics as to undergraduate students, we of course say that all Hamiltonians are Hermitian because that leads to unitary evolution, probability is conserved, all these wonderful things happen, we can solve things analytically. But of course, if you have dissipation in a system, then you know that you have non-Hermitian Hamiltonians, and then in quantum mechanics, we have a whole other machinery for dealing with such systems. A special case of non-Hermitian Hamiltonians are the so-called parity time reversal symmetric Hamiltonians, which are referred to as PT-symmetry, where the parity operator changes the sign of the position and the momentum operator, the time reversal operator changes the sign of the complex I. And these systems have received tremendous attention in recent years because they have a number of applications, in addition to sort of addressing some foundational questions in quantum mechanics. What we're trying to do in my lab is looking at exceptional points in non-Markovian systems, that is, exceptional points in time-delayed systems. And we're trying to see, are there applications for such systems? That's sort of the focus of what we are trying to do. But again, because it's a pedagogical talk, let me just sort of give you a toy model for what exactly is this PT symmetry and how do these non-Hermitian Hamiltonians arise and what are exceptional points. So let us assume that I have some sort of an integrated chip which has two waveguides, one of which amplifies light at a rate gamma, and the other one attenuates light at the same rate. And there is an evanescent coupling between them, so the light can leak back and forth. Sorry, was there a question?
Yes. Yeah. So in your previous slide, you mentioned that non-Hermitian H has the real spectrum. But in real sense, we have gone through a lot of quantum mechanics where we see one of the theorems is real Hermitian operators have real eigenvalues. And then if it is non-Hermitian, how do it preserve the time reversal and the parity?
Yeah, so I will show you in a minute. So you're correct that a Hermitian Hamiltonian will have real eigenvalues, and a non-Hermitian Hamiltonian, in general, will have complex eigenvalues. But in this very special case where this non-Hermitian Hamiltonian obeys parity and time reversal symmetry, it may have real eigenvalues, and I will show you in a minute why that is. All right?
Okay, sir.
So was there a follow-up or?
No, sir, you can continue.
Okay. So back to this waveguide picture, and what we do is, let's just assume I put light in from the top, and let's say I put it into the red waveguide, and as it propagates through this, some of it leaks into the blue, but in the end, some light comes out of both of these waveguides. Now I can simply write the rate equations, and so you can see on the left the subscripts 1 and 2 refer to the two waveguides. So if you for a second, let's just look at the first equation, and if you ignore the second term for a moment, you'll see that this is just the sort of the linear decay equation I just showed you, except it's with a positive sign. Just tells you that light is amplified here. Then the second term is just telling me that the electric field in this lossy waveguide is coupled to the gain. A similar equation can be written for the second waveguide, but now it has a negative sign because this one, the light is attenuated. So if I write this in a matrix form, I take these same two equations, I write it in this form, and the reason I do it is because now it looks very similar to an equation that we're all quite familiar with, where this vector here sort of is the wave function. I have an effective Hamiltonian here, and so the whole thing looks like the Schrodinger equation. This effective Hamiltonian, as you can see, is of course non-Hermitian. Now, but it is parity time symmetric. What the parity operator does mathematically is it interchanges the diagonal elements of this matrix. Physically, what the parity operator does is it interchanges the position of these two waveguides. So now the left one would be the lossy one, and the right one would be the amplifying one. The time reversal operator in quantum mechanics is antilinear. It changes the sign of the complex I. And so if you apply the parity operator and interchange these two, and then you change the sign of the complex I, you get back the original Hamiltonian. So we say it is PT symmetric. Physically, the parity operator interchanges the position of these two waveguides. Because gain and loss in optics are phase sensitive, then if you apply the time reversal operator, loss becomes gain, gain becomes loss. And physically, that is why we can say that this is a PT metric system. And so basically what it means is that the combined PT operator commutes with the Hamiltonian. Okay, so this is the Hamiltonian, and then this question that was just asked, its eigenvalues are given by the square root of the coupling squared minus this gamma squared. And this, as you can see, can have either real or complex eigenvalues depending on the relative values of kappa and gamma. Okay, but the behavior can be quite different depending on whether the eigenvalues are real or complex. So let's first take the case of the real eigenvalues. In that case, if I look at, so when I say intensity, you can just think of it as the norm of the wave function. Physically, I put some light in here, it's amplified, some of it couples in here, which is attenuated. So anyway, there's some bouncing back and forth. I look at the total intensity of light that comes out here as a function of time, and you can see that the total intensity stays bounded, even though the probability is not conserved. Okay, so this goes up to 4, but the total intensity stays bounded. But now if I go to the regime where the eigenvalues are complex, you can see that the intensity as a function of time just blows up exponentially. I don't know if you can see this exponent here. This is 10 to the power 8. Okay, so as you cross over from real to complex eigenvalues, you get this very sudden change in the behavior of the system, which we have tried to capture here. This is the norm as a function of this ratio of gamma to kappa. So when when gamma is equal to kappa, this is referred to as the PT threshold. And so until then, the intensity stays bounded, and after that, it shows a big change. And this was, exciting to people because anytime you have a sudden and abrupt change in physics, people start thinking of sensing. Oh, maybe if I sit at this point, then a small perturbation, kicks me over, and I get this huge change. So a small input produces a large output, and one can use all this for sensing. But so this is the crux of what a PT-symmetric system is. Now, in this model, and even though I called it a toy model, I want you to know that the people have done experiments on this. In fact, the very first experiments were on PT-symmetry were in systems like this, but it has some problems. One, loss is something that is intrinsic to a system. When these things are fabricated in clean rooms, there are inhomogeneities and material imperfections which give rise to loss. Gain requires external pumping. And so when you want to make the gain exactly equal to the loss, it's a challenge, to pump at the right amount and to get the gain and loss to be equal to each other. The other thing is, every time you want to change this coupling, which depends on the spacing between these two waveguides, among other things, you have to regrow a new chip with a different spacing between these two. So we were, just wondering, are there other ways of, a simpler implementations of a PT-symmetric platform? And then because of our interest in non-Markovian systems, what would the effects of a time-delayed coupling be? So we said, okay, let's replace this with something which looks very similar, which is I have two semiconductor lasers. I just call them SCL1 and SCL2, and they are separated by a certain distance, which translates into a time delay tau. Now, depending on what the separation between the two lasers is, in our case, and I'll show you experimental results here in a few minutes, the separation between the lasers is, the time scale is comparable to the natural time scales of the laser. The characteristic timescales of the cavity lifetime and the population inversion. And so we cannot neglect the time it takes light to go from laser 1 to laser 2 or reverse. So we bidirectionally couple these two. You can kind of see that it's the same picture as this. We replace the waveguides with two lasers. Of course, the one big difference is here, the coupling is transverse. Light is propagating in this direction. The coupling is here. But now the coupling is longitudinal. There are other big differences between the two systems. Waveguides are passive. And so these are linear systems. Lasers are, of course, nonlinear. You have a gain medium. You have a saturation of the gain medium, which is where the nonlinearity comes in from. You have, spontaneous emission. You have lots of other complications. So just by going from this to this, why should I think that this system would have any signatures of a PT symmetry. If you're interested in the details, we have been working on this for the past few years. Here are some references which sort of capture the essentials of what I'm going to tell you. But first, let's talk about this semiconductor laser. So I'm showing here a solitary semiconductor laser, and it has two degrees of freedom that describe it completely. One is the intracavity electric field E, and the other is its population inversion. And the time evolution of these equations are written in a slowly varying envelope approximation. So second order Maxwell block become first order equations. This first term here, alpha, is a material parameter. It's just a number between 3 and 7, depending upon the material of the semiconductor. And then this term here, this is if there is any feedback. So light comes out of the laser and goes back in. Okay, so kappa is how much of this feedback light is coupled in. This is the time delay. So the laser emits light, an electric field at time t, and it sees the same electric field after a round trip time tau. This term here, the exponential, is the phase accumulation as the light travels this distance. The second equation for the inversion, this is the pumping term, this is the spontaneous emission term, and this nonlinear term is the gain saturation term. This delay makes the system infinite dimensional, as I showed you on the first slide. So one of the things that will happen if I put this on a computer and solve this, in the absence of this term, so if I remove this, whatever is causing this reflection, if I neglect this last term, then of course the intensity as a function of time, you turn the laser on, it undergoes some relaxation oscillations, it settles to a steady state. If you look at N, it does exactly the same thing, but out of phase, because there's an exchange of energy between E and N. And so, but eventually everything settles to a steady state, and you can see that the inversion goes to 0. Now, in the presence of feedback, I plot again the intensity as a function of time, and look at the scale here. This one only goes up to 4 times 10 to the 4. This one starts at 6 times 10 to the 4. What it's telling you is that now, all of a sudden, this nice steady state behavior has gone into this really weird sort of chaotic behavior. In fact, if one does a time series analysis, one finds that this is indeed chaotic. So one of the things that feedback can do is it can produce a whole host of nonlinear dynamical events in a laser. And here I'm just showing you a special case where, just to make the point that time delay can produce some unusual behaviors. So now back to my system of 2 lasers, I couple them together. So I take so I have 2 lasers, so I write down 2 equations. So this is again, of course, with the material parameter. This is the coupling term. So E1 is coupled to E2 with a delay. E2 is coupled to E1. These equations are in the slowly varying envelope approximation, and they are written in a frame that is rotating at the average frequency of the 2 lasers. So I've got laser 1 at a frequency omega 1, laser 2 at a slightly dissimilar frequency omega 2, such that the detuning between them is delta omega. And this here is key. From laser 1's perspective, it sees a detuning of laser 2 by an amount E1 minus E2. From laser 2's perspective, it sees E2 minus E1. So it sees exactly the opposite sign. These are the population equation evolutions for the 2 lasers. So I'm going to take these 2, and I'm going to write this in matrix form. So it looks like this. Out here, I have what I've already shown you with the waveguides. This is a PT-symmetric Hamiltonian, which shows the properties of this abrupt transition from real to complex eigenvalues. So let's take this model here, and let's make 2 approximations. One, I just showed you in the previous slide that for any laser in steady state, this is true for all lasers, in steady state, the population inversion goes to 0. You need population inversion to get the laser to start lasing. But once it's lasing in the steady state, population inversion goes to 0. Let's also assume for a minute that the time delay is 0, so that I can neglect this term. Then this matrix ends up looking like this, and just compare the 2. They look identical. The difference is that now the gain loss terms are replaced by the detunings, and This is here, it's the coupling between the two waveguides. This is the coupling between the two lasers. The advantage of this semiconductor laser system is that as long as I have the two lasers operating slightly detuned from each other, I automatically have these two terms exactly equal and opposite in sign. Unlike with the waveguide, where external pumping has to make the gain exactly equal to the loss, here it's automatically ensured that the diagonal elements of the Hamiltonian are equal and opposite in sign. The other advantage of the semiconductor laser system is that the coupling in these systems is easily controlled with a variable neutral density filter, and so there's no need for regrowing a new system or anything like that. Now, of course, its eigenvalues of this matrix are just, you can see it's going to be real or complex depending upon the relative values of the coupling and the detuning. Okay, great. So now there are two questions. One, look, with the waveguide, because it was a linear system, it was all clear what's happening. Should I really expect a system that has these nonlinearities? I've made all these assumptions. Should I still expect the semiconductor laser system to show signatures of PT symmetry? So what I'm showing you here, so each column, you should think of it as a separate case. So in this very first column, let's first consider the case when the time delay is 0. So this is sort of the standard case. So this is how the effective Hamiltonian would look like. And what I'm plotting in these two so the time delay is 0, I'm plotting it for a specific value of kappa. I'm plotting the real values, the real part of the eigenvalues and the imaginary part of the eigenvalues as a function of delta omega. And remember, kappa is 0.1, so exactly at 0.1, the real part becomes non-zero, the imaginary part becomes 0. This is all expected behavior. Down here, what I'm showing you is I have solved that set of 4 coupled differential equations for E1, E2, N1, and N2. And again, I've set kappa equal to 10 gigahertz, which is in my scale units is the same as this 0.1. So this is where the exceptional point is. This is where I expect the eigenvalues to transition from complex to real. And you can see that on one side of this exceptional point, the intensity stays bounded. And there are two intensities here because there are two lasers, but they are identical, so the intensities lie on top of each other. So just look at the blue, the intensity stays bounded. You get to the exceptional point, you get this big jump. It is symmetric about 0 because unlike with the waveguides, detuning, you can have positive or detuning or negative detuning. The red line that I'm drawing through here, that is a detector averaged intensity. So these oscillations here are on the orders of gigahertz, but then if my detectors only have a bandwidth of about 1 gigahertz, so if I do a bandwidth averaging, I get this, get that behavior. Anyway, and then it's symmetric about both sides. But now in this column, I'm plotting the same things, the real and imaginary part of the eigenvalues, the bandwidth averaged intensity. This is all numerical simulations. But what I'm doing here is I'm neglecting this phase accumulation factor just to see what the effect of just the time delay is. What is the effect of this non-Markovianity? You can now all suddenly see that now, I chose gamma to be 0.02, so it's somewhere here. So again, the imaginary part is 0, but look at the real part. It shows, you see how it changes sign at multiple places. So this is a signature of the non-Markovianity, where now you're getting these multiple transitions, which when you look at the intensities of the two lasers, so now you can see there's a slight difference between them. One laser is in red, one is in blue, and this is detector bandwidth average. And here is the exceptional point. And you see in the vicinity of that, you get an abrupt jump. If I throw in the phase accumulation, it's kind of similar qualitatively, but quantitatively, there's a difference. These are plotted. These two are on the same scale. You can see that the transitions are much more frequent. And here you can see a dramatic difference. One laser is showing oscillations in the side bands, and the other one is not. The reason this happens is in order to vary the detuning between the two lasers, what we do is we hold the frequency of one laser fixed, and we scan the frequency of the other laser. So one that the laser for which the frequency is being scanned is in blue. The red is the one that is responding, and that's the one that shows all these transitions. This is the kind of behavior I should be expecting in my experiments, okay? Because in my experiments, there is simply no way for me to neglect this phase accumulation term. So while this theoretical result just shows me that, oh, look, this is the effect of the time delay, this is the effect of the time delay with the phase accumulation term also. So at least from the numerical simulations, it is apparent that the semiconductor laser model has exceptional points and that it shows this transition, this PT threshold where you get this abrupt transition, even though the laser system is very different from the waveguides because of its nonlinearities and the coupling between 4 different degrees of freedom and so on. So this is the experimental design. So there is, just a simplified version. There are 2 lasers. We control their detunings with by controlling the temperatures. So if we vary the temperature, vary the refractive index of the material, which then in turn changes the cavity length, which then in turn changes the frequency of the laser. And we take the light from laser 1, we couple it into laser 2. We do the same in the reverse direction. At various branches, we tap off for detecting frequency, wavelength, intensities, all kinds of things. And here are the results. So the way for you to look at this is to look at each column as for one particular time delay. So this is the separation, the distance between the 2 lasers. So this can be translated into a time delay. This top row is just showing you what I showed you just now. What are the real and imaginary parts of the eigenvalues? What do they look like? This row, this is the numerical simulation of the entire 4 set of laser rate equations. And it's a little bit hard to see, but I don't know if you can see this light green vertical line here, dashed line. I hope you can. But that marks the exceptional point. Okay, so no matter what the delay is, you'll see that on one side of the exceptional point, the intensity stays bounded. On the other side, it shows an abrupt transition. And that happens for all of these. There are, of course, differences in the details. As the separation between the lasers increases, this sideband transitions, you can see diminish in amplitude, and they become faster and faster. Down here are the experiments for the 2 lasers. These are all on the same scale. There are no fitting parameters. And you can see that, again, exactly at this exceptional point, you get this abrupt change. And so the semiconductor laser system seems to have this characteristics of a non-Hermitian PT-symmetric system. There is a well-defined exceptional point, and these features of the diminishing amplitudes and increasing frequency, all of that are captured in the experiments. Okay, so these time delay differential equations they don't have an analytic solution. Okay, there's even the simplest one that I showed you on slide number 1. You can't just solve it exactly. But there is a way to solve them using something called the Lambert W function under some approximations. And the Lambert W function is defined by the solutions of an equation of this kind. Now, of course, it has infinite solutions, but only 2 branches when k is 0 and 1, and -1 are real valued. So I can take this LK stands for the Long-Kobayashi model, which is my semiconductor laser model. If I throw away the nonlinear terms, I can reduce it to something that looks like this. In the details, you'll be able to find in this conference proceedings. So we are, at least under some approximations, we can reduce my semiconductor laser model to something that looks like the Lambert W function. So there's lots of details in here, just mathematical details. None of it is particularly complicated. In fact, if you are a student and you ever had to solve this problem in Planck's blackbody radiation, we always ask this as a homework problem. what is the, if you're looking at the black body density of energy density, what is the wavelength at which you get the maximum energy density? What is the frequency? You end up with a transcendental equation. That transcendental equation can also be solved by the Lambert W function. It has a very nice, elegant solution. If you're looking for another place to practice how to use the Lambert W function. Anyway, so we did it. So I want to, let me just go back a little bit and define something here so that I can use it with the Lambert W function. So supposing I define a dome width, so the intensity rises here at the exceptional point. The same thing happens in the opposite direction. So there's an exceptional point here, there's an exceptional point here, there's a separation between them. Let me just call that the dome width. Now, the exceptional point occurs when delta omega is equal to kappa, the coupling. Now, supposing I change kappa, okay? So instead of kappa being here, supposing I move it to here, then of course this jump in intensity will happen at this point. On the other side also, it will move back to the right, and so the dome width will increase. So if I keep changing kappa in this direction, then the exceptional point will move to the left here, and on this side it will move to the right. And so the separation between the exceptional points, which I call the dome width, will just keep on increasing monotonically with kappa. One of the consequences of this non-Markovianity is that if I look at the dome width using the Lambert W function as a function of kappa, we find that instead of a monotonic increase in the dome width, we still get an increase. The overall trend is to increase the dome width, and just look at this dark solid line. Ignore this one. You can see that it has these abrupt discontinuities. So then we looked at our numerical model, the 4-rate equations, and sure enough, I find it behaves in exactly the same way. And then when we do the experiments, we find the experiments also, you see the same trend. Okay. This, instead of a continuous monotonic change in the dome width as a function of kappa, this sort of behavior is a consequence, this discontinuous change is a consequence of the non-Markovianity. So the exceptional points have this rather unusual behavior. Okay, so I'm just summarizing what the effect on the dome width is. Finally, let me talk about the exceptional points in this system. So this is my original equation. I simply find what the characteristic equation is. You can see that it is transcendental. There's a lambda here. There's a lambda here. Okay, so fine. I make use of the Lambert W function, and what I do is I look for a critical detuning for which the eigenvalues are degenerate, and this whole piece here is the Lambert W function. And what I find is that if I plot this delta omega, this critical detuning versus kappa, along this entire curve A, these are all pretty much the exceptional points that we expect when delta omega equals kappa. You see, this is equal to 1. Okay, but there are some additional exceptional points along this entire line B. There are also these other exceptional points. So there are these sort of 3 distinct regions. When this kappa tau is less than 0.4, you have all these. So you see this little bit of space here. Okay, there's multiple exceptional points. And when this kappa tau exceeds 0.5, there are these isolated islands of exceptional points. In addition, some of these exceptional points are second order, and then there is a third order exceptional point right here at the cusp. Now, what the order of the exceptional points is important for sensing, and because the higher the order of the exceptional point, the more sensitive the system is at that point. But in a system that does not have a time delay, there would only be second order exceptional points. But here we have the possibility of a third order. There may be propagation, Hamiltonians, and PT-symmetric systems, exceptional points, and all these things that I wanted to get across. So this is one platform. A second platform is that we are using is what's called an optoelectronic oscillator. And some of you may not be familiar with what it is, so let me spend some time actually describing what an optoelectronic oscillator is. And we have published it in a couple of recent papers. We have another one that's in the second round of review. Hopefully it'll appear soon. But basically, it's kind of like a laser, but it has parameters that are much more easily controlled. So we start with a laser, and we run the light through a Mach-Zehnder modulator. And I'll tell you what this does. But it basically amplitude modulates the light. Then there's a long optical fiber, and the light travels through that. So everything that's in red is optical. So this is all light. This light hits the photodetector. The photoelectric effect converts it into electrons. So everything in black is an electrical signal. So this then goes into a bandpass filter. It gets amplified. We come out, we feed the output of the amplifier to the Mach-Zehnder interferometer. And this piece here that I'm running my cursor over, this is the optoelectronic oscillator. It's got an optical piece, it's got an electronic piece, and hence the name, an optoelectronic oscillator. And this thing behaves just like a laser. It has a threshold, you turn it on. If you have enough gain, it starts oscillating. The difference is that the output, instead of being an optical signal, is an electronic signal. And so it's a voltage, so it's much more easy to measure it and manipulate it and so on. So how does it work? Well, it's an oscillator. So here is my equation for an oscillator. You recognize the harmonic oscillator here, okay? And then there is some friction because I have a filter here, a bandpass filter, which attenuates, it's a bandpass filter, so it extinguishes some frequencies that are outside its bandwidth. So it essentially acts like a friction term. And then all of that is equal to the rate of change of the input voltage here. So one can obtain this equation just by applying Kirchhoff's laws to this entire loop. The negative sign is because we feed this in 180 degrees out of phase with the rest of the signal. So this is the model equation for a optoelectronic oscillator. So let's look at each piece of that in detail. So I first said there's a Mach-Zehnder modulator which amplitude modulates the light. Okay, so this is what the schematic of that looks like. You come in with some light, so that's the light from the laser, so that's E in. It gets split into two pieces, okay, so that's because we're making a Mach-Zehnder interferometer, and so I have these two, I apply a bias voltage to them, and then I recombine them. What the bias voltage does is it changes the path length difference, hence the phase difference, and if I modulate the bias voltage, I can alternately change the path length and modulate the amplitude modulate the output light. So I get, in addition to the carrier frequency omega naught, I get two side bands, one at omega naught minus omega RF, that's the frequency at which I'm modulating the bias, and omega naught plus the RF. So now when all of these hit the photodetector, remember there's this frequency, there's this frequency, and then there's of course the carrier frequency at omega naught. These two will beat with each other and produce a frequency which is twice the RF frequency. But omega naught minus omega RF will beat with the carrier omega naught to produce omega RF. This one will also beat with omega naught and produce omega RF. So at the end of the day, once you get through the bandpass filter, all that survives is the omega RF frequency. So that's how one makes sure that this optoelectronic oscillator, the frequency that survives within it is just the RF frequency. The photodiode is a standard reverse biased photodiode. So you just, you put some light into it and then you get some electrons and then it runs through. This V in here, that after the photodetector, that depends upon the amplifier gain. This cosine squared, this whole term, the cosine squared comes from the amplitude modulation, how the Mach-Zehnder modulator modulates the amplitude modulates the light. And here you can see the time delay. This is V out, which happened at a round trip time. So this uppercase T is this delay that's imposed by the optical fiber, and then this bias voltage is whatever is applied here. So I'm going to take this V in, put it into my model, and I get an equation like this where I have now scaled X1 and X2. Think of these as the voltages. Delta, this is the bandwidth of the amplifier, and here are the the gain of the gain of oscillator 1, gain of oscillator 2, and what I'm doing here is I'm coupling two such optoelectronic oscillators together. So here is one down here, here is the other one, and they're coupled through a hybrid RF coupler. So X1 is coupled to X2, X2 is coupled to X1. Here, X1 and X2 now are voltages that we're talking about. Okay, so in some sense, the model is very similar to the laser model that I just showed you. But this system gives me much more precise control over many elements of the entire coupled system. In particular, I can play with the phase of the coupling. And so you can see here that for now, I have a 180-degree phase difference. But because it's all electronic components, I can make this coupling real. I can make it imaginary. I can make it purely complex. I mean, I can do all kinds of things, but I won't go into the details of all those things for now. But very similar to the laser model, but it has some flexibility that I'll show you in a minute that I can't get with the laser. Okay, so theoretically, what we do is, so here are the same two equations I just showed you. I assume a solution of this form. I apply the slowly varying envelope approximation. I get my governing equation that looks like this. So here is what looks like the effective Hamiltonian. This is a non-Hermitian matrix. It's not PT-symmetric, okay, at least not yet. I mean, so I'm just looking at a non-Hermitian system. The coupling terms are here. Now, anytime you have these cosine squareds and things like that, one thinks of the Jacobi-Anger expansion. This is if you're trying to do an expansion of functions that have a trigonometric quantity in the exponential. So it leads to Bessel's functions of the first kind. So we assume that our amplifier has a small bandwidth, and we neglect any nonlinear terms that fall within the amplifier. Okay, so if we do all this, then we essentially get a condition on, so remember, this thing behaves like a laser. So what are the conditions on the gains? Alpha 1 and alpha 2 are the gains of the two oscillators, the net amplification factors. Right at threshold, just before the oscillator turns on, what is the frequency relative to the filter center, and what are the gains? So we get two conditions. And so I have sort of put together this summary slide. So if you just get this out of this whole optoelectronic oscillator discussion, that's enough. This is generated theoretically, but it contains a lot of information in it. So let me go through it in some detail. What I'm plotting along the x-axis is the gain of oscillator 1. Alpha 1 equal to 1, that's the threshold. Below that, if alpha 1 is less than 1, oscillator 1 does not turn on. As soon as it exceeds 1, oscillator 1 is on. The same thing with oscillator 2. Okay, it has a threshold at 1, so this is scaled in such a way. Okay, so what is this showing me? It is showing me many things. One, these green curves that you see, these are the thresholds. These are the values of alpha 1 and alpha 2 for which this coupled system just begins to oscillate. So it's like a laser threshold. One way to think about this is, let's pretend that alpha 2 is 0, and I just increase alpha 1. If alpha 2 is 0, that means I only have one oscillator, and that one oscillator stays off until I reach alpha 1. Beyond alpha 1, it comes on, okay, and just, it operates in a steady state. The color is a constant. It just, it puts out a certain amount of RF frequency, and the same thing happens along this axis. But now, this line here, this dashed line, this is if the time delay is 0. And this dashed curve here is if the time delay is infinity. And for our experiments, and then for these simulations, therefore, we have chosen the time delay to be 185 nanoseconds, which is closer to the infinity. This piece, this curved piece, that remains the same no matter what the delay is. 0, infinity, 186 nanoseconds, it doesn't matter. That threshold remains the same. This solid black line here, this is an exceptional line. What that means is that everywhere along this, there is an exceptional point. Now remember with the laser model, I did not have a line all the way across. I had these isolated exceptional points. In this system, everywhere along this, there is an exceptional point. There are regions like this black where the laser shows power bistability. It turns on and off depending upon whether I cross from the blue to the black or from the gray to the black. In this magenta region, the laser shows tristable frequency, and in this region, in the white, it's bistable frequency, and this red curve here on both sides, this is a fold bifurcation, which in the language of nonlinear dynamics, essentially means that two stable and an unstable attractor come together and annihilate each other. But the point is that all these boundaries that I've drawn here, each of them represents a transition. And if you cross that boundary, you get a very abrupt change in either the intensity or the power of the combined oscillator system or in the frequency of the combined oscillator system. That's why a map like this gives us lots of information about where these boundaries lie. And if I cross these boundaries, I can get a dramatic change and abrupt change in behavior, which can then be used for sensing. Just so I will now, just to emphasize the point, just show you that here is the green is the threshold. These are the exceptional lines. The point at which the threshold and the exceptional line meet, these are the critical points. And these happen when alpha 1 and alpha 2 are 1 plus or minus 1 over the square root of 2. Okay, so for example, here, alpha 1 would be 1.7 and alpha 2 would be approximately 0.3, and the reverse would be true at this other critical point. The red, as I told you, is the fold bifurcation, and then this alpha 2, this is this long expression that I skipped over. But in this region, so if you cross from the gray to the black, you get amplitude sensitivity. If you cross from anywhere into the white, you get frequency sensitivity. So a very rich system. It's got exceptional points. It's got a time delay. It's got these sensing capabilities. So it's got all kinds of things. So I'll just show you a few experimental results. But I keep reproducing this map because you can compare it to that. So here are the experimental results for these two coupled oscillators. And so here is the threshold in green. So that's for 186 nanoseconds. This is what that is. So you can see this piece here is that, and so on. The red is the fold bifurcation, and this color map is showing you what the RF output power is. Now here, I'm showing you what the frequencies are for these, because remember, I'm saying here, I have multiple frequencies here, I have two frequencies here, I have a single frequency, so all these things. So the way to think of this picture is, if you're trying to imagine what this 3D plot looks like, just think of it as a fish with an open mouth that's facing you. Another way to think about this is if I go across this 45-degree line here, that's the alpha 1 equals alpha 2 line. That would be this line here. So as I go along this line, once I cross from the gray to the white, I go into this bistable frequency region. So that's what along this line, the frequencies are bistable. I get either frequencies down here or I get frequencies up here, but nothing in between. Out here, this is the magenta region where I have a tristable frequency regime. So if you look at, so there'll be 9 of these curves, 9 of these dots along here. So each triplet corresponding to one possible tristable state. So the experiments then are, they sort of reproduce all of the features that one sees from this theoretical calculations in this map. This is how things look in this blue region. In this blue region, it's like there's a single oscillator. There should be a single frequency. And sure enough, this frequency offset, I mean, what is the offset from the bandpass amplifier? So you get the oscillator oscillates at a single frequency that is equal to the frequency of the amplifier. In the bistable, so you see I've labeled them E, so that's, in this white region, I said you get two frequencies, and sure enough, you get two which are equally offset from the filter frequency. Now, I want you to know that this is truly bistable. In other words, both of these frequencies don't appear at the same time. On a single shot, I get either this or this, and we've just taken two such shots and superimposed them on top of each other. But otherwise, it's truly bistable in the sense, depending on what the noise levels in the system are, and there are lots of noise sources, Johnson noise, Nyquist noise, all kinds of things. It'll bias it towards one frequency or the other, but both frequencies are equally likely. So I've labeled this D. So now I'm close to the magenta region. And again, there are two different colors because you get a frequency comb of one color or the other. So this is where you get this tri-stable frequency regime, and you get a frequency comb that again, so if I were to be crossing from here to here, if I had so in this white region, I would have a bistable frequency. If a signal triggers me to go into the magenta, I would switch from that bistable frequency regime to this, and that becomes an indicator of my frequency sensitivity. Now I'm going to show you what happens in this black region, which I'm calling the bistable power region. In bistable power region, we see a hysteresis, and the hysteresis, I'll explain physically what it means, and then I'll show you what the data is. Let's say I'm sitting here, and I cross from, so here the system is off, okay, so that's the gray region is off. And then as I cross across the fold bifurcation, because of the size of the basin of attractor of that off system, the system remains off for some time until it turns on. Now, if I go in the reverse direction, it's on, and then because of the size of its basin of attraction, as I turn it off, it stays pegged to that on state before it turns off, and that gives rise to a hysteresis. So we're showing you that here in these plots. So these are experimental plots, the output power versus the two gains. And what we're doing here, I'll just focus on this for a second, is we fix the value of alpha 1 and we scan alpha 2, and we get this whole surface here. But these bold lines here, those, and it's the kind of the same idea here. I'll connect it to these pictures at the bottom. So you see this line here, that's this point that's running at 0.3. So basically I would be holding alpha 2 at its critical value, and I'm sweeping alpha 1. So let's look at this. This green path here is this green path, okay, what's called path 2. Now let's come here. This path here where I'm scanning alpha 1, that's this path here. Okay, so that's this. Similarly, if instead of scanning alpha 1, so here I'm holding alpha 2 at its critical value and scanning alpha 1. Here, if I hold alpha 1 at its critical value and hold alpha 2, then from these two plots, you'll get this behavior. So you can see in both cases, there is a hysteresis, which again, anytime we have a hysteresis, we know that as long as the signal is wider than the width of the signal, of the width of the hysteresis loop, it will trigger it from one state to the other. And so that's a mechanism for using it as a sensor. So we did use it as a sensor. So what I'm showing you here is the output power as a function of the input power. We're holding alpha 1 at its critical value. We're changing alpha 2. And remember, alpha 2 equals, at 1 would be the critical value. So we're approaching the critical value. As we approach the critical value, the system becomes more and more sensitive to very small perturbations. So for small values of alpha 2, fine, I put in some input power, I get some output power. It's pretty much linear, so it's not particularly interesting. But then at about alpha 2 equals 0.77, you see this abrupt jump here. So there's a nonlinear increase in the sensitivity of the system. And let's now get to 0.88, which is this blue curve. You can see it's become extremely sensitive. It, in fact, even shows a spurious jump here. But then if my input signal is about let's say this is minus 68 dB or so, then the output is about 5 dB. So 68 dB becomes about 5 dB. So that's more than a 60 dB enhancement. Okay, so that's 60 dB. It's a log scale, so that's a million-fold enhancement of or amplification of the input signal. In fact, we have turned this around and we have seen how sensitive, how small a signal can we measure, and we find that given what the size of our cavity is, the system is sensitive enough to detect about 0.2 photons. Okay, so what that means is that if there's one photon every 5 round trips on average, this system is sensitive enough to pick it up. Now, what about the bandwidth of the sensitivity? Well, this is it for different. So as you can imagine, as you get closer and closer to the critical value, it becomes more and more sensitive. In other words, the bandwidth keeps narrowing. So if I look at the 3 dB point, so this is approximately 25 dB. If I come down to about 22 dB, you can see that that's just on the orders of a few kilohertz. Okay, so it's a very, very sensitive detector. It can detect very weak signals in a very narrow bandwidth. And this happens because the system has these critical points, which again is where the exceptional line meets the threshold curve. Other ways of using it as a sensor. So, what we do is we put in a control signal and we turn the control signal on here. As soon as we turn the control signal on, which is in red, the intensity of the oscillator jumps. And then when we turn the control signal off, it turns off. So I'm just showing you a blow up of the same thing here. So again, the very weak signals, you can see on the scale here that it's, this red piece is not the signal. That red is to indicate that that's what's blown up here. But the control signal is this straight line here. So you can see that it's, very, very small compared to what the output is. So again, it's because we're sitting at these critical points and these exceptional points that you get this tremendous jump in signal. So I want to finish up by just telling you that, if you have these non-Markovian systems with a time delay, they lead to a very rich landscape of behaviors, all of which can be controlled by controlling the time delay. I showed you 2 examples. One is the coupled diode lasers. I glossed over this point that system is actually what's called an anti-PT system, as opposed to a pure PT system. But it was not important for the point I was trying to get across. But if you're interested, I can, an anti-PT is a system in which the PT operator anti-commutes with the Hamiltonian of your system. And that's what happens in my diode laser system. I also showed you a non-Hermitian platform in coupled optoelectronics systems. It connected all of these to the exceptional points that arise in a non-Markovian system, and then showed you a couple of examples of RF sensing with an OEO platform. With that, I thank you for your attention, and I am happy to answer any questions you may have.
I have a few questions, so thank you very much for
Sure.
a very interesting and informative talk. So in quantum optics, we use Mach-Zehnder interferometer for identification of phase change. I mean, how sensitive it is to the change of the phase by using different states, Gaussian, non-Gaussian, and non-Gaussians are more sensitive. So in your case, did you study quantum version of your model?
No, we did not. And to be honest, I don't know quite how to do that. Okay, it has many elements which are purely classical. For example, I have a bandpass filter, and which is purely classical. Okay, so to represent that in a quantum formalism would be an artifact. It would be artificial. Or let's just take the Mach-Zehnder interferometer itself. Okay, if I were to sort of purely look at this on the quantum version of this, I would have to say, okay, let's say maybe one photon comes in at a time, and so on. At that point, the noise in my system from the amplifiers and just the Brillouin scattering and the fibers and all these things, I mean, these are all just too large for the quantum effects to really be visible.
Mm-hmm. Okay, my second question, do you use any nonlinear optical effects in platform number 2? I mean MZI.
So
optical
by
nonlinear effects.
Yeah, you mean are there nonlinear effects, or do I actually use any of them?
Yes, maybe Chi3 effect, or maybe something like that.
Yeah, so we keep the intensities low enough. So the Chi3 would come primarily from the fiber, okay, because we are using actually a fairly long fiber. But we go anywhere from 2 meters, which may not be that long, all the way up to 30 meters. And the reason for that is the longer the fiber, the higher the quality factor of my
scattering
oscillator. Yeah, but we keep the intensities low enough that the Chi3s there's not much of Brillouin scattering or any dispersion.
Mm-hmm. Okay, thank you. This is one comment. The matrix 2 by 2, I mean, equation which you used in your calculations, I see quite often in micro-ring resonators, they split this frequency from the non-resonance to the non-resonance by applying similar techniques. So it's good that I have seen another application of such mathematical applications of that.
Yeah, you make a good point. In fact, we are also now using some of these ideas that people have done with chirality in micro-ring resonators. Yes. Exactly the idea that you're talking about, in order to look at chirality in our system. Chirality comes in many forms. It can be in polarization, it can be in frequency, it can be in power, and our system has all of those features in it. And most of the time, chirality is studied in the context of clockwise and counterclockwise modes. We are doing it we don't have counter-propagating modes, but we do have this effect of frequency splitting as a function of the nonlinear gain. So it's an ongoing experiment actually at the moment on chirality in these systems.
Thank you.
Yeah. Any more questions?
Yeah, Gautam, I have a couple of questions.
Sure.
How are you?
Good. It's good to see you. I don't know if you were there at the beginning. I said I remember being in that room. Where
Yes, I was there. Yes. See, Gautam, what did you get for?
Sorry.
Hello.
Sorry, I said Gautam. I am also here. I said.
Anantha is here.
Okay, it's great. It's great to see old friends. Old, I mean not in age, just in time.
Yes. See, I'm just wondering, what did you get for a general non-Hermitian system?
What did I get means, you mean just very broadly, what do I get out of them? Or?
See, for the general non-Hermitian system, what did you get? I mean, in terms of eigenvalues.
Okay, so my optoelectronic oscillator is what I consider a very general non-Hermitian system, in the sense that it is not a special case of being PT-symmetric or anything like that. Okay? And the reason I am interested in this very general non-Hermitian system is it also has exceptional points. And my focus is, but in addition to exceptional points, it has these critical points where, the fold bifurcations, it has these additional dimensions to it, which arise when you couple non-Markovianity with non-Hermiticity. Okay, so the answer to your question is, what I get out of it is I get this exceptional lines behavior that you will only get for the standard non-Hermitian system, the PT-symmetry or special cases, you will only get a unique finite set of exceptional points. Here I can get, along that alpha 1, alpha 2, in that landscape, I can get, in effect, an infinite number of exceptional points. I can get exceptional lines, I can get exceptional surfaces, so I have a lot more flexibility in a generic non-Hermitian system.
Let me ask one more question. So, could you please explain why, you are using electrical components also instead of totally optical components? So, any reason for that?
Yeah, so if everything is optics, then it's analogous to just a pumped laser, right? So a dye laser, for example, or a titanium sapphire laser is just, it's kind of the same idea, except that I have a pumping laser, and then I have all, a cavity with light that's going through it. Now the problem with that is, or not the problem, but what I want is as high a Q factor with as low a phase noise as possible. The optoelectronic oscillator, I can have a very long optical fiber. Okay. And as you know, the longer the path length, the shorter the delta nu is, and so the larger the Q is. Okay, so I can have and then the phase noise in an optical system will always be much greater than in a purely electronic signal. Okay, so those are the reasons why we go to this. We go to the electronic regime.
Thank you.
Because if I keep everything just optical and I amplitude modulated the light that is circulating inside the cavity will still be an optical frequency, which means I would still have to convert it down to an electrical signal to measure it. Okay. Which then comes with its own, with added noise and things of that sort. Whereas if I completely operate in the electronic regime, I don't have those issues.
But I think with micro ring resonators, you will have more flexibility. You can use them, for sensing applications and for selection of separate or specific frequencies which you need resonance frequencies, and you can kill non-resonance frequencies. So maybe it's better to use, but I don't know why you are using fiber instead of micro ring resonator in your case.
Oh, because I'm using fiber because if I want to make, let us say, a 30-meter long micro ring resonator, in other words, I want the path length to be 30 meters.
Yeah.
Okay. Then because of the insertion losses and the input and output coupling losses, I'm never going to get 30 meters of an optical path length. Okay.
Yeah. Okay.
So that's number one. Number two, you're correct that a micro ring resonator can be used is useful for at certain frequencies.
Yeah.
In my case, of course, I'm sure for everybody, much research is driven by what your funding sponsors want. In our case, the Air Force is interested in detecting radio frequency signals, and RFs are best detected using using another RF technique. So that's part of what it is. The final piece I would say is this time delay for a micro ring resonator, because you're dealing with the speed of light. Okay, the delays are not going to be of the same magnitude as what I can get with electronic signals.
Thank you.